Yes, so first of all, I would also join the other speakers and thank the organizers very much for giving me the opportunity to speak here in this really excellent and great conference. And yeah, I will talk about probing systems of ultracold matter. And so a typical cold atom experiment looks like this. So you have to engineer your Hamiltonian, so typically some potential landscape, let's say a lattice like this. Then you prepare your state, so you have to load atoms into the lattice. So often you want to prepare some state close to the ground state. Then you apply some experimental sequence, and this could be, for example, something like this. So you modulate your potential so that you pump, let's say, the atoms to one direction. So this is, I will not talk about charge pumping, this is just serves as an example. And then you probe your system. And the elementary and basic type of probing that you have at hand is usually you image the real space density of your atoms. And if your resolution is high enough, like in quantum gas microscopes, you can really image and count the number of atoms in the different lattice sites. So now the question is, can you get more information? I mean, of course, there's a way you can get more information and you know about them. But let's assume we have prepared a band insulator state, like in such a charge pumping experiment, where we have a fermionic system that fills the lowest band of this lattice system, and we want to probe this state. So the state is given by, let's say we have two sublattices, A and B, like in this lattice. Then you can write it down as a superposition of momentum states Ka on the A sublattice and quasi-momentum state on the Kb lattice. And their relative weight is given by an angle theta, and their relative phase by an angle phi, and this corresponds to a Bloch vector for every point in K space. And now if you want to measure what state you have, then obviously the density is not enough. So the density just gives you information about this theta angle, so the relative occupation of these, but not about the phase between them. And so how can you get, and this phase requires knowledge of off-diagonal elements of the single particle density matrix. So how can you get this information? And there is this very famous ancient technique of quantum gas physics, which is time-of-flight imaging. And in time-of-flight imaging, what you do is, so you do your experimental sequence, and then you probe and when you want to probe your system, you switch off all the potentials that trap the atoms, including the lattice, and let them fly. And in this time of flight, free expansion, sort of the momentum of an atom transforms into the distance it travels. So if you wait long enough so that this distance is much larger than the original extent of the atoms, your real space density corresponds to the momentum density. And this obviously contains off-diagonal information. And for our particular example is you can show that you can get something like this. So now the phase enters here, the phase azimuthal angle, but you still cannot get a full tomography of the state because you have both this factor of both theta and phi in combination. So in order to get it, some years ago, so it's not sufficient to reconstruct it, with Philip and Maciek, we came up with an idea that if you could implement sort of an extra azimuthal rotation, delta phi, and you could monitor sort of this signal with respect to delta phi, then you can get theta from the amplitude and phi from the phase of this dynamics. And then you can get a full tomography of the state. And how do you get this extra delta phi? So you have a second stage before you do the time of flight, where you quench into a Hamiltonian where you have a strong offset between A and B, and this just leads to a pseudomagnetic field in this pseudo-spin space given by the sublattice, and you rotate your state just a little bit further. And this technique has been used extensively in the group of Klaus Sengstock and Christoph Weitenberg in hexagonal lattice systems. So they measured the Berry curvature in momentum space of such a lattice insulators in such lattice Hamiltonians. They observed dynamical phase transition, which was also visible in this momentum signal. And recently they measured the Chern number of a target Hamiltonian into which they quenched the system. And this is, of course, very important because adiabatically preparing a topological non-trivial state is not easy because you have to cross a phase transition. In this way, they were able to measure the Chern number. And now, this is the starting point of this talk is that this idea of using sort of quenches to different types of Hamiltonian before you probe your system or before you measure your system, that this can be a useful idea to get information about the state of your quantum system. And I will present some ideas about along these lines. And so the outlook is first is about how to measure the single particle density matrix in real space basis, in such also in inhomogeneous lattice systems, how to measure localization of pre-thermal Floquet states. This is work together with David Wells' group from Santa Barbara, and a scheme how to measure intrinsic topological properties of Floquet systems. And there is other work, of course, that along similar lines. So this is by no means an exclusive list. So I talked to Jörg Schmiedmeier, and they put something in this direction on the archive last week together with Jens Eisert. So it's just that what came out of these ideas in our group. Okay, so the first piece I want to present is how to measure the single particle density matrix. And if you have a lattice system, let's say it's inhomogeneous, might be disordered, and you have some state in this system, how could you measure these matrix elements? They are quite important, or it would be quite nice to have them, because once you have computed them, they give you all information about all single particle observables in the system. But they also contain signatures of many-body physics, so they give unique signatures, for example, of many-body localization. So this is a paper by Jens Bardason and co-workers, where they looked at the spectrum of the single particle density matrix in some finite disordered systems, and you see that this gap here is really a signature of the localization of the system. They have not been measured yet on distant lattice sites. You can measure them on neighboring lattice sites. Of course, you can measure the diagonal matrix elements, which are just densities, but on distant lattice sites, it turned out it's to be difficult. And the scheme I'm going to present exploits the high spatio-temporal resolution you have in quantum gas microscopes, as you heard about them in Immanuel's talk, and Christian Groß will talk about it also tomorrow. So just imagine you have a lattice. Let's say it's spinless fermions, but generalization to hardcore bosons or to spinful fermions is straightforward. They occupy a lattice, and then you want to compute this object between some lattice sites A and B. And the rules that you have to apply is that you can create on-site potentials, and you can measure on-site occupations. So, of course, the first thing you want to do is you want to couple them. The naive way or not the naive way, the natural way is to realize that we are some second order process. So you raise the energy of the middle sites, and then you have some second order process via the states of this channel here, and then you get some effective coupling matrix element. But unfortunately, if you do it like this really goes down exponentially with the distance, so it's completely useless if you go to distances, let's say more than 3 or something. And so the reason for this is simply you have many channel states and their sign oscillates, and they just give rise to destructive interference. A way out of this is if you structure your channel in a clever way, namely by sort of introducing some barriers at the edges, and then in the middle have some sites whose energy is close to this A and B subspace, and in this way you can single out a single channel state which predominantly leads to the coupling, and then you can get something like 1 over m. I will not go into the details here, but you can really see if you compare the coupling for the homogeneous channel with that for the structured channel that it's much better, and you can also show that you have this law. Okay, so now you have created an effective Hamiltonian like this. Additional to the coupling, you can also make an offset here. Now let's first concentrate on the case where we have a single fermion. We will come to the other cases in a minute. Then you can find a pseudo-spin realization, pseudo-spin description of this system. Up and down corresponds to atom on side A and B. You have this effective Hamiltonian. the reduced density matrix giving you a single particle density matrix is characterized, is of this form and characterized by some Bloch vector R, which corresponds to the polarization. If it is shorter than 1, which is generally the case, it's a mixed state. And the target now is the single particle density matrix, which depends on the x and the y component. And what can we measure? We can measure the z component, which is a pity. But of course, we can now use sort of this engineered Hamiltonian to perform rotations along the z-axis and the x-axis. And in this way, after the rotation, you can get a result, z polarization, that depends on the initial x and y polarization. And you can get your single particle density matrix in the single fermion case. And if you go beyond the single fermion, you measure you do the same protocol, you measure NA and NB, and you distinguish between the cases where you have 0, 1, or 2 particles. If you have 0 or 2, you know the contribution to this is 0, so that the total single particle density matrix is given by the frequency of the single particle events multiplied by this quantity that we determined by the method just explained. Okay. And this you can also generalize to spinful fermions in 2D systems and hardcore bosons. For spinful fermions, you just have to measure different spin components on both lattice sides, but I will not go into the details. Okay, so the second part is about measuring localization in a pre-thermal Floquet system, and this is joint work with David Wells' group, and actually also it's David's group that really triggered this project here. And let me first give you a crash course on thermalization of Floquet systems. So Floquet systems are systems which are described by Hamiltonian, which is periodic in time. And if you sort of take a many-body system of that type and you let it evolve, and it will relax to some steady state. And the question is, can we make some statements about this state? So first of all, there are generalized steady states in this system, which are Floquet states. They consist of a Floquet mode, which is time periodic, and a quasi-energy, which characterizes this phase factor, similar like an energy. The time evolution of an arbitrary state can be expressed in terms of these Floquet states here. So the coefficients just depend on the projection of your initial state onto the Floquet states. If you look at the evolution of the observables, you see you have two contributions. One is the dephasing of the quasi-energies, which is very similar to the physics of a non-driven system. And you have also a time periodic part, which is called micromotion due to this, these Floquet modes. And in the long time average, you can argue that by dephasing, the non-diagonal terms vanish, and then you expect that your observable will synchronize with the drive, so you get an expectation value which is completely periodic in the generic case. And this expectation value is described by a generalized Gibbs ensemble. Is described by a diagonal ensemble where you can get it by taking a density matrix whose probabilities are just given by the square of these factors here, these coefficients here. And then comes a non-trivial step. So there is a conjecture that this diagonal ensemble can be described by a Floquet generalized Gibbs ensemble, where the state is described completely by the number of integrals of motion in your system of conserved quantities. And this has been tested numerically, and this is believed to be the generic situation if you have integrals of motion. And for an ideal gas, we will consider as one example in the following these integrals of motion are just the occupations of the single particle Floquet states. And if you have on weakly interacting systems, this might still be an approximation for sort of a pre-thermal plateau which you reach before the dynamics moves on to some other physics. And the most generic case, if you have no integrals of motion, is really an infinite temperature state, because in a Floquet system, not even the energy is conserved. So this is why it's not even a Gibbs state. Okay. Now in the protocol we have in mind, so we start from some undriven Hamiltonian, prepare the ground state, switch on the driving abruptly, wait for a while, switch back to the undriven Hamiltonian and measure or estimate or find a bound for the ground state occupation of the system. Then looking at the evolution of this system, we can see that these coefficients are given by the overlaps between the projections of this ground state onto the Floquet modes, and they correspond to the expectation value of this projector here. And now, assuming we have reached a steady state, we can employ our diagonal ensemble, and we can see that since these ground states appear both in these coefficients and in the expectation value, we get the fourth power of the overlap, and this is an inverse participation ratio. So it measures the number of Floquet states needed. I mean, it's an order of the number of Floquet states needed to represent our ground state. So it's a direct measure for localization of our ground state in the basis of Floquet states. And of course, this tells us also something about the localization of Floquet states in the basis of our original eigenstates. And now, the experiment in David's group goes as follows. So you have an optical lattice which is amplitude modulated, and they can really achieve very large modulations because they create this lattice by actually superimposing two lattices. And they load bosonic lithium-7 atoms, which have tunable interactions, and in particular, they can tune the interactions to 0 so that we have the ideal gas system I was mentioning. And then the ground state we start from is a Bose condensate in the k=0 mode of the lowest band. And now we can also measure or estimate this ground state overlap with the ground state by just looking at the occupation in the lowest band in the k=0 mode, which they can achieve doing band mapping after the sequence. And so this fraction of atoms, in this mode is a direct measure for the localization. And now this is a typical experimental sequence. So if they start to drive the system goes down very quickly to this plateau type situation, which is very well described by a simple theory for a non-interacting gas, which is the dashed line. And so you can clearly see this plateau. It's consistent with the theory, as I said, and it's just a few states which are occupied, just a few Floquet states, which you can see here. It's something like 2 or 3. And this also explains these wild oscillations because it's not really in a thermodynamic limit. I mean, this is why you see these oscillations. And why is it just such a few number of states? Because quasi-momentum is conserved. And so you have a discrete number of states, and the level splitting even becomes larger when you move up in energy. Okay, so you can plot these occupations where the driving frequency, where they're in unit of omega 0, which is roughly the distance between the two lowest bands, and the driving strength. And again, we see quite good agreement between theory and experiment. We can also look at the dynamics for longer time. So this was 200 microseconds. This is now dynamics up to 50 milliseconds. And then you see that there is a second plateau reached for, let's say, the yellow and the red dots, which correspond to non-interacting and weakly interacting system. And we don't understand this plateau right now. It could be to the occupation of further transverse modes in the system. This would make a lot of sense, but it actually means the system doesn't completely delocalize. So it's still a finite number of modes. However, if the interaction is much stronger, and this is the blue region, on this time scale you really lose your atoms in the lowest band, and this corresponds to delocalization. So it's a transition from an localized to an ergodic type of behavior, which you can quantify using these arguments. Okay, so now let me come to the last part, which is about measuring winding numbers that characterize intrinsic properties of topological Floquet systems. And this is a work together with Nur Ünal. She's also here, a postdoc of mine, and Babak Serajeh, who's he spent a sabbatical at our institute. And again, we consider a lattice system, and it's driven periodically in time. So we can again describe it. It has again some Floquet states, And now these Floquet states are Floquet-Bloch states because the system is translational invariant, and they have are characterized by sharp quasi-momentum k, and some index n, which is a band index. And these Floquet states are eigenstates of the one-cycle evolution operator of the system, and the eigenvalues are these phase factors, which are characterized by the quasi-energy. And this quasi-energy, or this dimensionless quasi-energy here, is defined modulo 2 pi only because, of course, if you have this phase factor and you take the logarithm, you can take one of the branches or whatever branch you want to. And now, if we look at topological properties of these systems, there is some nice effect due to the fact that these systems are driven, which has been pointed out in these papers here by Kitagawa and co-workers and Ratner co-workers. So if you take a strip geometry and you look at the Floquet spectrum, you can have, for example, cases like this, where you have two bands because you have two sublattices, and they have Chern number 0, and there are no edge modes at all. But there could be also topologically non-trivial bands, which are characterized by a finite Chern number, as it was also introduced this morning by Jacqueline Bloch. And this indicates that there are some edge states living in the gap between these modes, and they would sort of be states which are topologically protected and give rise to chiral transport along the edges of the system. So this is quantum Hall physics. But now in the Floquet system, there is other possibilities. Namely, you could have edge states in this gap because the spectrum is periodic. So you have essentially two gaps between these two bands. And then you also have a finite Chern number. And if you have sort of modes here and here, you can even have a situation where the Chern number is 0, even though you have topologically protected edge modes. And the Chern number just gives the difference between modes leaving the band on the upper side and entering on the bottom. And so the Chern number is not sufficient to characterize these topological properties of this driven system. And therefore, Ratner and al. Introduced spatiotemporal winding numbers, which live in the gaps, and they count the number of edge modes. And the Chern number is just the difference of the winding numbers on top and bottom of this band. And these are, and while the Chern numbers are integrals over K space, over the two-dimensional momentum space, and the integrand is given by some combination of the wave functions, these are really integrals over three-dimensional space given by time and quasi-momentum. So they contain all the information of the driving as well. And measuring them, therefore, is extremely difficult. I mean, it's already difficult to prepare a topological non-trivial state which is characterized by a Chern number and then measuring just this two-dimensional quantity, but really making a tomography of all of this is really, really difficult. And so the question is, how can you do it? And the recipe that we're suggesting is the following. So you create a family of driving protocols with varying frequencies, omega, and let's say these frequencies are characterized by this driving period tau, and the one you're interested in is one member of the family. And then you have these Hamiltonians here. Then you measure the quasi-energy band gaps by just ramping into this Hamiltonian and observing the K-resolved dynamics. So then you see you have a spectrum like this. This is the Floquet spectrum for a particular case versus tau, and this is the quasi-energies. It's actually a system for a system as it has been realized in Klaus Engstock's group. So it's a hexagonal lattice which is shaken and where you have some resonant coupling between A and B sublattice. But that's just the detail. So the ideas are completely generic. So the next thing is you have two band gaps here. You have a pi band gap and you have the 0 band gap, and you know that the pi band gap is the one that gets large when you go to high frequencies, so when you make tau small. So this is why you can really reconstruct the spectrum. Second, you notice, one can notice that the winding number changes through band touching points. So here we see band touching points at 0 quasi-energy and another one at pi here. And we also know in the high frequency limit that this pi winding number is 0. since in this limit we can compute everything using time-averaged Hamiltonians, and in this case, the physics cooks down to the physics of undriven systems, so there cannot be any winding number here. And then you can check this. So this is sort of these are the band touching points. This is how the spectrum with respect to K looks. And then you can look at the spectrum on striped geometries for this type of drive, and you see that here it is trivial, no edge modes. Here, after this band touching at 0, you get a band pair of edge modes in the middle of the spectrum in this gap, and then you get another pair after this second band touching. And now the question is, how do we reconstruct, just 2 slides, how do we reconstruct in which way this winding number changes? And for this, we can employ the following strategy. So if you take the one-cycle evolution operator, and you can parameterize it versus kx, ky, and tau in this vector lambda, and then you can linearize it around the band touching point. And this gives rise to this matrix S here, and it has been shown by Nathan and Ratner in the context of phase bands, which is a theoretical concept, which is a different way of interpolating. It's between different bands. That the change of the winding number is given by the sign of this determinant. And this is a very robust quantity. So it can easily be measured. So we adiabatically prepare the Floquet state in the vicinity of these band touching points. Of course, you cannot go adiabatically through the band touching, but you can prepare them in the vicinity easily. Then you can reconstruct these Floquet modes there that you find by using the tomography scheme I was mentioning at the very beginning, and from this you get the evolution operator, and then you just need to do it on 6 points around it, and you can go even quite far away from this point because this is such a robust quantity, and it works very nicely. So with this, I would like to conclude. So this is the summary, what we did, and I just flashed some results where we created some, we have a scheme how to create local magnetic fields in an optical lattice system, also using quantum gas microscopy techniques, and we can do charge pumping in 2D Chern insulators, and we can really determine the path where the charges go. So they can go like this, or they can go like this by just changing the vector potentials which we ramp. But if you're interested in this, you can look at this publication. And with that, I thank you very much.